Well, I thought it was only appropriate to play and strum the chords to the Eagles, take it to the limit, since we're going to be talking about definitions of limits today. So, this is a really technical section right here, so we just try to cover it to give you an idea of what the formal definition of a limit is to kind of get you started on that. We do some fairly basic proofs. And to begin with, before we uncover the technical definition of a limit, I want to work out some absolute value inequality problems because these relate nicely to the definition of a limit. So if you had the absolute value of x minus 2 is less than 4, the meaning of this problem is to find all numbers x so that if you find the distance between x and 2, the distance will be less than 4. Okay, so this thing right here is just the distance. And remember, an absolute value is a distance. When you're subtracting two numbers, you're getting a distance when you do the absolute value. So that's the distance between, some number, just an unknown number, and 2, and that's going to be less than 4. So what we're going to do on this is I'm going to show you how to do this with a number line and then how to do it algebraically. So let's start by just putting a dot on 2. And we're going to go out 4 units because of this. So let's just go out 1, 2, 3, 4. So we're going to go out 2 units or 4 units like that. And then we're going to go 4 units below, 1, 2, 3, 4. So we would end up having basically a solution would be on this interval like this. So basically all the numbers that have a distance between a number and 2 of less than 4 units would fall between -2 and 6 on a number line. Okay, so we would say the solution is the interval -2 to 6. Okay, and just think about this. If you took any number, like if you took 3, the distance between 3 and 2 is 1. Distance from 4 and 2 is 2. Distance from 5 and 2 is 3. Distance from 6 to 2 is 4. So that's where those distances are going to be. The way that you may have learned how to solve this type of inequality in an algebra class is you may have learned that, well, this distance falls between 4 and -4, and then you can add 2 to each part of the 3-part inequality. So you would end up having -2 less than x less than 6. Okay, so that would be the answer to the problem. That's in interval notation, and that would be in inequality, just in set builder notation. Okay, so we're going to do several of these problems. This next problem is going to say the meaning of the problem is to find all numbers x so that if you find the distance between x and 5, the distance is less than 2 units. So what I'm going to do on this one is a similar thing. We're going to put a dot on 5, and then we're going to go up 2 units and down 2 units like that. So we go up 2 units, that would put us at 7. And then if we go down 2 units, that would put us at 3. So it looks like the answer to the problem is going to fall between the interval 3 and 7. Okay, so we'd write our answer in an interval notation as the interval 3 and 7. Okay, and then if you were to do this algebraically, if you have a less than problem like this, what you do is you just put the x minus 5 in between 2 and -2 to start with. Then you solve that 3-part inequality by adding 5 to each part. So you would get the same answer. We would get 3 is less than x is less than 7. Okay, so that's how that goes. All right, so this is important in the definition of a limit. I'm going to let you go ahead and do number 1 yourself. Okay, I'm going to try this. Go ahead and do this problem. Okay, so this is what you should have come up with on this. This means absolute value x minus 6 less than 3. The meaning of the problem is to find all numbers x, so that if you find the distance between x and 6, that distance will be less than 3 units. So we're going to put a dot on 6. That's the starting point there. And then we're going to go up 3 units, which would take us out to 9. And then we'll go down 3 units from 6, which would take us to 3. Okay, so that's all you're doing on that. So that means that that would be an interval between 3 and 9. So we would write this in interval notation. Our answer would be written as 3 to 9, like that. So that's where those distances are. So you're 3 above 6 and you're 3 below 6. And again, if you did this algebraically, absolute value x minus 6 less than 3, you just put the x minus 3 in the middle of 3 and negative 3, and then you can add 6 to each part, and that'll give 3 less than x less than 9 like we thought we would get. Okay, so I just want you to know the meaning of that problem because it's a part of the technical definition of a limit. Okay, now we're going to look at the formal definition of a limit, and I'll read it to you, and then we'll do some activities that'll help you make sense of it. Generally, to a beginner, the limit definition is a little challenging to get, certainly at first glance. So basically, if you have the limit as x approaches a of f of x equals L, this is true if for every number epsilon, and that's the Greek letter epsilon, for every epsilon greater than 0, you have a positive epsilon. There is a corresponding number you can find, delta greater than 0, such that the distance between the function and the limit value is less than epsilon when the distance between x and the limit value is between 0 and delta. So a couple of things. The Greek letter D is delta. Okay? So one of the things that you want to kind of maybe make a note to yourself right here, this part right here is really giving a distance between the function and L, which is the value of the limit. Okay, so it's the limit value like that. Okay, and then this right here is giving a distance from x. So it's a distance between x and the value you're interested in on the limit, which is a like that. Epsilon is a positive number. Delta is also a positive number. Okay? So really, we usually write it like this. For every epsilon greater than 0, there is, or you can find a delta greater than 0, such that if it's true that x minus a is between 0 and delta, then we can conclude that f of x minus L, that distance, is less than epsilon. That's very hard to make sense of unless you begin to look at some diagrams and some activities that will help you with this. So what I'm trying to do with this picture down here is, this is some arbitrary function right there. That's f of x. And then this is the value of the limit. Okay, so what we're looking at in this picture is the limit as x goes to a of f of x is equal to L. So this is the limit value. Now epsilon is some positive number above and below that limit value. So it makes kind of a band, an epsilon band right there you can think of. Okay? And then if you follow that down to a, then delta is a positive number a little above a and a little below a. So you end up getting a delta band, okay, like this. So when I look at this, you can kind of think of this as going down for a plus delta would be kind of the end of that band, like that. And then epsilon would develop kind of the bandwidth of the region around L. So L plus epsilon would be here, L minus epsilon's there. So the idea would be that you can find a value of delta that falls within that band no matter what epsilon is. That's the idea. Now, what I'm going to do is we're going to do some activities that'll help you understand this a little bit better then. So a couple of things on this then is for any epsilon greater than 0, you can find a delta such that this happens whenever this happens. Okay, so that's the idea. So given any epsilon, you'll be able to find a delta, and that's a small number around the value of a that will exist, okay, regardless of what epsilon is, okay? So what we're going to do on this then, this means that to determine a relation between delta and epsilon, so for any vertical distance epsilon from delta, there is a horizontal distance delta, so that the distance between x and c is less than delta, such that the distance between f of x and L is less than epsilon. So I'm going to go to the next page, and we're going to do some activities that will help you begin to make sense of this. So sometimes when you're learning this, it takes a little bit of time to really get a firm grasp of what's going on this problem then. So we're going to do a couple of activities that'll help you with this. The first thing on this particular problem is what you're given is we're interested in the limit as x approaches 3 of f of x is equal to 5, and we're going to do this for epsilon being equal to 1, and then again we'll repeat it for epsilon equals 1/2. So epsilon is some positive number, and what I've done on this is we're interested in a function, in this case, just some arbitrary kind of function. We're looking at some sort of a linear function because it's a little bit easier to interpret. Okay, so what we're going to do on this is, again, what the definition says. It says if you do x minus 3, the distance between x and 3 is between 0 and delta. We're interested in the distance of f of x and 5, the value of the limit, is less than epsilon. So that comes directly from the definition of a limit. So what we're going to do is this. Epsilon is a vertical distance from the value of the limit. So the value of this limit is 5. So the first thing I want you to do is make a note that that's what L is. And what we're going to do is we're going to go up 1 because epsilon is 1. So we're going to go up to 6, and then we're going to go down to 4. So what this is doing is this is really, this thing right here is 5 plus epsilon. And this value right here is 5 minus epsilon. So you're doing that. Now what we're going to do is we're going to follow over to the graph. So we're going to go straight over from that point, which goes there, and then we're going to go straight down to the x-axis, and then that will give us what we call the delta belt. Okay, so we have that. So we're interested in A is that value right there. So delta is going to be that distance right there. And then we're going to do the same thing here. We're going to go follow this over to the function. Then we're going to go straight down. So then you would have this. So this point right here becomes A plus delta. And A is 3. So if you look at that, that's A. And then this value right here is going to be 3 minus delta, like that. So you end up having this bandwidth right there. So the idea is as you close in and make epsilon smaller, the delta belt will also be smaller, but you'll be able to find a delta belt that will satisfy that condition. So we're determining a value of delta. So delta in this case is going to be this distance from here to here. So that's 2. So in this case, for part A, we would have delta is equal to 2. So we're going up 2 and down to around that when epsilon is 1. So it's kind of like when epsilon is given as 1, then we conclude that delta can be 2 or less. Okay? Then we're going to go to the next one, and we're going to do basically the same thing. Again, this is the value of your limit. Okay, the limit of f of x, that's your L value right there. So we're going to make a note that that is L. Now this time, epsilon is going to be 1/2. So what that means is we're going to go up 1/2, like this, so just go up 1/2, and then we're going to go down 1/2 like this. So what that's giving is that's giving the value of the limit, which is 5 plus epsilon. And this right here is giving you the value of the limit minus epsilon. So we're going up 1/2, down 1/2 like that. Then we're going to follow over to the function, which goes there. And again, this is A is 3. So we're kind of interested in that. And then if we go straight down, we're going to get the value of 3 plus delta. Okay, A is 3, 3 plus delta. Now we're going to go back here. Again, we're going to follow the function like that. Then we're going to go straight down like that. And that value right there is going to be 3 minus delta. So what we conclude on this now is delta is that distance right there. So delta is going to be equal to 1. Okay, so what we conclude is our conclusion is delta is equal to 1 when epsilon is equal to 1/2. So as epsilon gets smaller, we're still going to be able to find a delta, a positive number delta that will fit within that. And what we have is we kind of got a belt here. Okay, this is kind of that part right there gives you the epsilon belt. And this part right here kind of gives you the delta belt right there. So no matter what that epsilon belt is, you should be able to find a delta belt within those values. So that's how that activity should help you a little bit to begin to understand a definition of a limit. Okay, the next one, moving on to number 9. Okay, what we're doing on this, we're going to determine values of delta from a graph. And the function is given, again, this time we're given the function f of x. We're doing the limit f of x as x approaches 2 is equal to 5. Okay, so we're going to determine the largest value of delta satisfying each statement. So it's very similar to the last problem. So the idea on this is first of all, if you take the distance between x and 2, that should fall between 0 and delta. Delta is a positive number. That kind of gives that delta belt. Then if we do the distance from the function and the value of the limit, which is 5, that should be less than epsilon, like that. So we're going to do a similar kind of activity. The thing on this is you're given epsilon. Okay, so that's what epsilon is. And this particular thing right here, and that inequality, that's epsilon. So the first thing we're going to do is we're going to look at epsilon equals 2, and then in the second situation, we're going to look at epsilon equals 1, and see if we can find a value of delta, the largest value that we can use that'll satisfy that condition. So we're going to do a very similar thing to the last problem. This is, the value of this limit's 5. So that right there is, that's what L is. That's the value of the limit. So the value of that limit is 5. Since epsilon is 2, that means we're going to go up 2 units, up to 7. And then we're going to go down 2 units to 3. Okay, and that right there would represent the value of the limit 5 plus epsilon 2. And then this would represent the value of the limit 5 minus epsilon. So that gives you that epsilon belt then. So then we're going to follow this over to the function like this, and then this right here gives you that epsilon belt that I'm going to just sort of shade in like that. Okay, then what we're going to do is we're going to go straight down from these values. So I'm going to go straight down here to get that delta belt. Okay, so that's going to 3, and then this one is going down to 1 like this. Again, this is what A is. That's the value you're interested in the limit. So what this is that's going to be 2 plus delta, and then is what that point is. And then this point right here is going to be 2 minus delta. So you would end up having your delta belt would be like that. Okay, so what your job is to find the largest delta that we find on that. So the largest value of delta is the distance from there to there. So that largest value of delta would be equal to 1. Okay, so the answer to this problem would be delta equals 1 would be the largest positive value that we could use on that then. But we could use smaller values. As long as delta is below 1, then we're going to fall within that band. Okay, so that's kind of the idea on that. Okay. Moving on now to the next one. Okay, moving to the next one. Now we're looking at epsilon equals 1. So we're going to work with this. Okay, so we're going to do a similar thing here. So again, the value of the limit is 5. So that's your limit value. Now, since epsilon's 1, we're just going to go up 1 unit right there. Okay, and that's going to be the value of the limit plus epsilon. Then we're going to go down 1. That will be the value of the limit minus epsilon, so this will create our epsilon belt. Okay, so we're just going to follow over like that, and then this right here is going to be the epsilon belt. Okay, we're just taking a region around the value of the limit of plus or minus 1. Okay, then we're going to follow straight down. You've got to be kind of careful on this. So we go straight down. That looks like that's about 1.5. And if you go straight down on this, that looks like that's going to be about 2.5. So that delta region is going to be between 1.5 and 2.5, like that. Okay, so what that means then is your value of A is at 2, so that you basically have A is 2, and then you have 2 plus delta, and that's 2.5, and then you have 2 minus delta, which is 1.5, so that means that delta is going to be half a unit up, so we have that as our final answer. Okay, so that's how that works out. Okay, so let's see. We're going to, I'll let you go ahead and try let's go ahead and do one more, then I'll let you try a few of these. Okay, so with this next one here, we're looking at this limit. So we're looking at the limit as x goes to 2 of f of x equals 4. Okay, and what this means, this distance between x and 2, you write that distance between x and 2 between delta and 0. And then you write the distance of f of x and the value of the limit. We know that that has to be below, whoops, I did that wrong. The value of the limit's 4. So we're going to say the distance between the function and that is 4. That's less than epsilon. So again, we're going to take some basic values and do that. So we're going to find the largest value of delta that satisfies these statements. So this is an epsilon value right there. That's also an epsilon value there. So we're going to look at epsilon equals 1. And then in this graph, we'll look at epsilon equals a half. Okay. All right, so let's take a look at how this goes. So again, the value of this limit is 4. Okay, that's what L is. So I'm going to write that as L is equal to 4. If epsilon is equal to 1, then we're going to go up 1 and down 1. And again, this right here would be the value of the limit plus epsilon. This right here would be the value of the limit minus epsilon. And then we can follow over to the graph, and that will give our epsilon belt then. Okay, now we want to follow straight down. So we want to go straight down to get our delta belt. So we make it to 1. And then if we go over here, we're going to make it to 3. Okay, so what we're doing is we end up kind of with this. Okay, this is the value of A is 2. That's A. So this really represents 2 plus delta. And that right there represents 2 minus delta is what that is. So what you have is you have your epsilon belt, which I'll kind of shade in the yellow color there. And then your delta belt is going in here like that. Okay. So what we would have on this is delta would be just 1 unit above 2. So we would conclude that delta, the largest value of delta, would have to be 1. Epsilon's 1, delta's going to be 1 or less. So that's the answer to the problem. Okay, then the next one, same limit. Okay, we're interested in the limit of 4. So that's the limit value. Now this time epsilon's a half. So what you're going to do is go up a half of a unit. Okay, and then that right there is going to be 4 plus epsilon, or 4.5. Go down a unit. That's going to be 4 minus epsilon, or 3.5. So we're going to follow over the function. And we're going to follow straight down to get this delta belt. Okay, so we'd be like at 1.5. Then if we follow over like this and follow straight down, that's going to give that value of 2.5 like that. So the idea is the epsilon belt would be there. The delta belt would be the horizontal distances like that. Okay, so what we end up having is, see, basically this is A, this point right here is a, which is 2 plus delta, okay, and that's really going to be equal to 2.5. And then this value right here is going to be 2 minus delta, which is going to be 1.5. So that means the distance from 2 and 2.5 is 0.5. So then we would conclude that delta, the largest value of delta, would be 0.5. And then that would be the solution to that problem then. Okay, so that activity is really a good way to help students begin to understand the technical definition of a limit. Okay, now I'm going to go to the next one and let you try the next two problems and see if you can reason these out okay. These are curves on here instead of lines, but you should still be able to figure these out okay. Okay, so let's see how we did here. So this time I've given you this expression, giving you the value of the limit. So we have the limit f of x as x goes to 3 is equal to 6. So again, the distance between x and 3 is going to be between delta and 0, and then the distance between f of x and the value of the limit, 6, is going to be less than epsilon. Okay, so what you've been given is you're given epsilon is 3 for this graph, and then we're going to change that to epsilon equals 1 for this graph, and you're going to find the largest value of delta where that condition holds then. Okay, so it's just a matter of, look at this. This is the value of your limit. Okay, the epsilon belt, you're going to go up 1, 2, 3 to this point, and then that will be 6 plus epsilon, or 9, and then go down 3. So that will be 6 minus epsilon, or 3, like that. So we're adding epsilon, and then we are subtracting epsilon to make that belt. Okay, we're going to just follow over the function. And then we're going to go straight down to get the delta belt right here. So we're at that point right there, which is 5. Then we're going to follow over here, which goes there, and then straight down, which gives that value of 1. So what you have is, this is A, and then we're going out delta above and below. So this point right here would be 3 plus delta, which is equal to 5. And then this point right here would be 3 minus delta, which is equal to 1. So that means delta has to be 2. Delta is the distance from here to there, so delta is equal to 2. So we would conclude on that delta equals 2 is the largest value, and if delta is smaller than 2, then we're guaranteed to be within that belt. So again, what we have is, this is your epsilon belt right here, and then your delta belt would be this region and here like that. Okay, so that's what you should have came up with. Now what this is attempting to show you is, if epsilon gets smaller, then delta is going to get smaller. So in this case, this is the value of your limit. Your limit is 6. Now this time we're going to go up 1, and we're going to get the limit value 6 plus epsilon, which is 7. Then we're going to go down 1 to get 6 minus epsilon. And then we'll follow straight over to the curve to get our delta belt. Then we go straight down to the x-axis, so that looks like that's going to be at 3.5. And we go here, follow over to the curve, go straight down to get the bottom of the delta belt, which looks like 2.5. Okay, so what we have on this then is the value of A, which is 3 again. Okay, so delta, you're going to have 3 plus delta, which is going to end up being 3.5. And then this point right here is going to be 3 minus delta, which is going to be 2.5. So that means delta in this problem is going to be 1/2, is what you should have came up with. Okay, then again, same idea. This is your epsilon belt. Okay, like that. And I think I went too far on that. Yeah, it should be like that. So let me erase that. Okay, and then the delta belt is going to be in this region right here, is what you should have came up with then. Okay, All right, going to the next problem. I want to make sure you got this okay. So you're given the limit as x approaches 4 of f of x is equal to 5. So what this means is the distance from x and 4 is going to be between 0 and delta, and then the distance between the function and the value of the limit is going to be less than epsilon. So in this case, this is epsilon. Epsilon is going to be equal to 1 in our first graph, and then in our second graph, epsilon is going to be smaller. Epsilon is going to be 0.5. Okay, so we're going to start off again with, this is the value of your limit, right there. That's the value of your limit. If epsilon's 1, you're going to move up 1 to get 5 plus epsilon, and you're going to go down 1 to get 5 minus epsilon to create your epsilon belt. And then if we follow over the function, and then down to the x-axis, we should get the width of the delta belt. So that's 7. Follow over here, straight down like that, that would be 1 like that. And of course, this is the value of a like this. So what you have then is this is 4 plus delta, which is 7. And then this point right here is 4 minus delta, which is 1. So that means delta's got to be equal to 3. So the largest value of delta in that case is going to be 3. So again, here's your epsilon belt. And then your delta belt, all doing the blue, is falling between 1 and 7. So you're able to find a delta based on whatever value of epsilon that you get. Okay, then following to the next example here, we're just going to start the same way. Here's the value of the limit, which is 5. Epsilon's a half, so we're going to go up there to get 5 plus epsilon. We're going to go down 1 to get 5 minus epsilon, and then follow over to the curve, all the way over like this, and then down, so where you should have ended up was 5, 6, 6.5, and then if you follow this, you should be there. Okay, down like that. Let me make sure I got that right, so I think we're good. Okay, so I kind of redid this. I was off a little bit. I was having trouble seeing that. So if you go up to delta, so that would be like 5 plus epsilon. And this would be 5 minus epsilon would be that point. So if you follow straight over, you get a delta being from 6 to 2 like that. So this value right here we would say is 4 plus delta, which is 6. And then this value here, we would say 4 minus delta, which is 2. So delta then has to be equal to 2 as your largest value of delta. And again, delta is the distance from 4 to 6. So that's equal to 2. Okay? All right, so hopefully that helps you begin to get an understanding of what's going on this limit definition. The next thing I'm going to do is I'm going to pull up a website here in just a minute that will display this pretty well. Okay, so what I've pulled up here, this is a GeoGebra applet, which is a pretty nice applet here to show this definition. So what I want to kind of have you focus on here is we're interested in the limit as x approaches a. This is the value the limit's approaching. So if you went straight up and over, this would be the value of the limit. Now what we're doing is we're making epsilon be equal to 1 to start with. So that means if we went up from this point up 1 unit, we would be up in here. And if we went down 1 unit, we'd be down in there like that. And we kind of form this belt. So the idea is going to be, it'll find a delta for us given this epsilon. So I'm going to close in on that a little bit. So if I close in and make epsilon smaller, you'll notice that this distance around here kind of closes in. So I'm going to close that in. You can see that value right there. That's your epsilon belt. Epsilon's a very tiny number, 0.2. So if we followed that over, like we were doing in the previous activity, onto the curve and down, we should be able to find a delta that falls within that region. So if I take the delta smaller and smaller, I'm going to be able to find a delta that falls within there then. Okay, so this is the epsilon bound. and then this is the delta right here. So it doesn't matter how small epsilon is, we're going to be able to find a delta to close in on that effectively then. And again, we can do different things on this applet. We can change the value of A. So if I was interested in, say I'm interested in A is like 2.2 or something like that. Okay. And then if I'm interested in the value of a limit, then I should be able to find, create a delta belt around that then. So this is a pretty good applet. These applets are not the best. This is not bad. So if your limit was equal to 0.7, then what would happen is if this is the value of your limit, then your delta belt should be in there. So you'd have to move the value of A over there to get that, created within that value like that. So that's what that applet does. So it does a pretty decent job of showing that. Okay, now here's a little bit better applet that I like. This is some sort of a function, and this is the value of the limit when x approaches a. So again, epsilon I can change. Right now I've got epsilon right at about 1, right at 1, a little bit above 1. This is the epsilon belt, so you're adding epsilon, subtracting. So if you followed epsilon over, then we'd create this delta belt like this. Okay, so the idea is now delta, if I make delta too big, it's going to change colors. Right now delta's too big, but if I squeeze in, then we know that we're within range. So if I make epsilon smaller, okay, now I'm out of range with my delta belt, but if I make delta smaller, then I have found a value of delta for that epsilon. If epsilon's 0.56, we need to be kind of in this range. And I can continue to close in on epsilon. Now I'm out of range, so that means delta needs to be smaller. So now I'm in range. Okay, so if epsilon's 0.30, if delta's, we found a delta. Okay, then if I close even further and further and further, I can keep closing and I'm finding a delta. There's 0.09, there's 0.06. I can go even smaller, and then I can close in like that. So now there's epsilon 0.04, there's delta 0.01. So that's a great applet that shows how this does, I think, very well. So that's what the definition of a limit is trying to show you. Okay, on the next illustration is, I went ahead and used the graphing calculator to help me with a couple of things on this. So what we're looking at is we're looking at the cubic function x cubed plus 3, and I went ahead and just drew two graphs there. We're interested at the limit of f of x is equal to 3. That's pretty easy to see. So if you're doing the limit as x approaches 0 of the polynomial function, and polynomial functions are always continuous, so you can just plug in the 0 and evaluate the limit to get 3. So what we're going to do on this is we're just going to do a similar thing. First of all, this is the value of the limit, and let's look at epsilon being equal to 1. So again, if we were to go up, move up 1 to 4 like that, that would be like 3 plus epsilon. And then if we went down 1, that would be like 3 minus epsilon. So you're creating your epsilon belt. Now if you went straight over like this, and then straight down, it looks like maybe we're at 1. Okay, and then if we went over like this, we'd have to go over to the graph like this to get to that point, and then straight down, that looks like maybe we're between, our belt is between negative 1 and 1 if you look at this then. Okay, so what we have then is you're going to find a delta such that f of x minus 3 is less than epsilon. So it looks like on this particular thing, delta could fall within negative 1 to positive 1 like that. So delta would just be, the biggest delta would be 1, and if delta is between 0 and 1, then it will satisfy that epsilon. Okay, and then the next one's the same thing. This is the value of the limit is at 3. If epsilon is 0.5, we're going to go up 0.5. We're going to follow over to the function like this, and down like that. That looks like that might be falling to 1. Then if I go down 1, and then down 1 like that, that looks like that's between negative 1 and 1. I may not have done the the last one exactly right, but I think I'm pretty much on that. I'm going to show you on a graphing calculator how you can get this exact in just a minute anyway. Okay, so I'm going to pull up my calculator and we'll take a look at how we can do this. So we're going to put in x to the third plus 3. And we're going to graph that on a pretty small window. We're just going to look at a little bit around this. Let's go like for x minimum -2 and for x max let's go up 2. Like this, and then let's go a scale of 1, and then for y let's go from say 0 to 4 by a scale of 1, and then draw a graph like this. And what I'm going to do is I'm going to use my technology to find this a little bit better. So if epsilon is 1, then you're going up from 3. The value of that limit is 3. So we're going to go up to 4. So what I'm going to do is I'm going to take my window actually up to 5 now that I'm thinking about this a little bit better. So let's take that window up to 5. Okay, now let's draw a graph of this then. Okay, so we've got our cubic function, and then epsilon is going to be 1, so we're going to go up from 3 to 4, and then down from 3 to 2. So I'm going to put in 2 more graphs. I'm going to put in 4, which is above the limit value 3, and then 2, which is down 1. So we're going to create the epsilon belt on our calculator then. Okay, like this. Now what we need to do is we need to find these intersection points right here to find these delta values. It looks like -1 to 1. So what I can do is I can go second trace, and I can go option 5 to intersect, and I can get the intersection values just by closing in with the cursor key fairly close, like this. So I'm going to do that, just kind of get fairly close to that intersection value. Okay, so let it move a little bit there. I can press enter. The next curve, I can get it fairly close to the intersection point. Then when it says guess, press enter. So notice that intersection point is equal to 1. So that would be the largest value in the delta belt would be 1. Then if I started this over again, and if I did intersect again, now what I need to do is I need to take my cursor way down to the left, and sometimes this graphing calculator doesn't keep up very well, so I got to move this way over here like this, and sometimes my calculator crashes when I do stuff like this because it just doesn't keep up with my mouse very good. So I need to get closer over to that. Gosh, this is painfully slow when I do this on this TI emulator. It's just ridiculous. Okay, because I got to get close to it. It'll jump back to that intersection point right there. So I'm going to move over here. I'm going to go ahead and press enter because I'm getting a little tired of this. Okay, so I'm going to press enter. It'll stop here in a minute. See, it's trying to keep up with my mouse clicks. God, that's like a snail. That's freaking ridiculous. Come on. Okay, come on, stop. Stop. Okay. All right. Now what I got to do is I got to take down. I got to get this mouse. I got to get that down there. Now, this is driving me crazy. It's just this calculator emulator is so bad on Windows 10. It's so slow. Okay, so let me try this other intersection point here again. If it doesn't work, then at least I think you'll get the idea. That's just this calculator is so bad. Okay, so I'm going to try to get to that intersection point. Okay, so now it's supposed to go down to that bottom curve, but it's not doing that. There we go. Well, it jumped there, now it jumped back. Okay, so I got to be on the first curve, second curve. There we go. Now I'm going to press enter, and then I'm going to close this thing in like that. Now I'm going to press enter and just see if it works. There we go. It found it. So that is -1. Okay, so that verifies that on that particular problem. Now on the next problem that we're doing, okay, we made epsilon 0.5, so what we would do is we would change this to go up not to 4 but to 3.5. So I'm going to make this 3.5 like this, and then I'm going to make this 2.5 like this, and then I'll find those intersection points. This is a little bit hard to do, but this will make this much more accurate. So if I find one intersection point, because of the symmetry, you're going to find the other one anyway. So this is going to give you your epsilon belt. And then if I go second, trace, option 5, intersect, let's just press enter. Let's press enter. Press enter and see if it jumps over to that intersection point. So that is going to intersect at about 0.8. Okay? So that value is not 1, it's really about 0.8. Right? So what you'd end up having with this one, based on what we saw on the calculator, is that thing comes down to a delta is around 0.8. Okay, so you got to use technology on that. Okay, right? And I'm going to do one more of these things with technological approach, and I'm going to pause this just a minute and get this set up. Okay, to finish this up, let me pull up my calculator, and I have put in the function. My window is this. I'm going to put this over here just for my reference on my window. Okay, so I've got my window set, and we're going to do this problem totally with the calculator. A couple of things I want to show you on my graph is we're interested in the limit as x goes to 24 on this particular problem. Okay, so if I was approaching 2, so if I go through and take my calculator and just trace out at 2. So I'm going to trace at 2, I'll just show you that that's 24. Okay, so that's what the limit is. So we're going to let epsilon be equal to 1 in this first diagram right here. So it's pretty hard to do this just by tracing and eyeballing it. So what I've got to do is, okay, the value of the limit's 24. If epsilon's 1, then I'm going to make that go to 25, and then this will be 23. So we're just going up 1 and down 1 from the 24, and what that's going to do is it's going to draw a couple of lines for us to establish this epsilon belt then. Okay, then I'm just going to do intersection points. So I'm going to go second calc, option 5 intersect, and I'm going to close in on this right intersection point. So I'll press enter. Now we want it, the second cursor to be on the red, so we're on there. So I'm going to press enter, then guess I press enter, and it's going to give us that value being about, and I'll write this down for further reference, that's about 2.42, about like that. And then if I repeat that, just over again with the, and then go option 5, this time I need to close in on the intersection, the left intersection point. So I just move my cursor. God, that thing is so slow. Okay, come on, stop. That's close enough. That's good enough. Okay. Now I'm going to go, I have to do my down switch to get to that black line. Now guess, press enter, and then it'll give this being around 1.58. So that means that, you know, the value, if you follow that limit, is going to come from between those two values like that. So delta would be, you know, approximately 0.42 or less. If epsilon is 0.1, delta would be around that region like that. So delta would just have to be a positive number less than about 0.42 if you did that. Okay, now I'm going to close in and I'm going to make epsilon 0.5 and do the same thing. So what I would do on this, instead of making this 25, I would make it 24.5. Okay, like that. And then I would make this 23.5. And if I graph that, that just, you'll just see the epsilon belt it's closed in a little bit more. And then we can find those values of delta with the intersection command again. So we're just closing in a little bit more on that. Okay, then again, what I'm going to do is I'm just going to go second, and you could even zoom in on this if you wanted to. I'm just going to leave it the way it is. Option 5, get fairly close to this. Press enter. And let's see, the intersection's about 2.24. So in this case, we're about 2.24. So the delta belt's getting smaller. And then if I repeat it for the second curve, go option 5. This time you just got to close in a little further to this point. Okay. It's going to ask for the second curve, so that's the first curve. Second curve, you need to go down to get it on the black. Press enter again after guess, and now that's taking you at about 1.76. Okay, so what's happening on this then is at a equals 2, the delta values are just going to be between, delta is going to be a little less than 0.24, and it's going to be some positive number like that. Okay, so that's the idea. You'd have to be within those boundaries like that. So you can use technology to find a delta for a given epsilon if the limit exists. So that's the idea. Okay, so I'm going to do this recording in 2 parts. This will be the end of part 1. Part 2, we'll do a few proofs.